Welcome everyone. This is our third episode in our sensors and microcontroller interfacing video series. Here in this video, I am going to show you how to convert the resistance variation from the thermistor to its corresponding voltage variation. We are following a project-based approach in the video series. You can watch the whole video series to get better understanding of our design workflow. But if you have good understanding in any of the videos, it doesn't matter. You can jump over the video you are interested on. You can find the whole playlist link in the description below. Here in this video, we will apply circuit principles to convert the resistance variation obtained by our thermistor into corresponding voltage variations.
If you like the video and find it useful, please give me your like so that YouTube can help me recommending it to others. Subscribe and set the notification bell to all for more of our future videos.
Many sensors like strain gauges and temperature sensors like RTDs and thermistors convert the physical variable like strain or temperature into small changes in resistance. But we need the environmental physical variable variation in the form of signal so that it can be understandable by a microprocessor or a microcontroller and be suitable for electronic measurements. As we know, signal is in the form of either current or voltage. So at this stage, you should understand that the resistance variation from the thermistor should be converted into its corresponding voltage variation. There are two ways of doing this are the voltage divider and bridge circuits. Our thermistor, which we are using in our project, converts temperature into resistance. To understand how this is done or to understand the characteristic behavior of this, you can watch our second episode by clicking right above here. The simplest conversion of resistance into voltage is by using this circuit configuration. The two resistors connected in series and fed by voltage source Vs. And one of the resistors is our sensor. In this case, R2 is our sensor and the voltage through the sensor is, by using voltage divider rule, VR is equals to R2 over the sum of the two resistors R1 and R2 times the voltage source Vs. So this way we can convert the resistance variation of the sensor to the voltage VR. But even though this circuit is simple and uses smaller number of resistors, it couldn't give reliable output voltage for weak signals from the sensor. And sometimes we need the output voltage start from 0 to some specified value. But in this case, as the voltage source Vs is fixed, the voltage offset below or above 0 cannot be avoided. So another way of getting reliable and offset-free output voltage, we need to design a Wheatsone bridge circuit. A generalized bridge circuit consists of four impedances Z1, Z2, Z3, and Z4 connected in such a way that the voltage source is fed in those terminals and the output is taken from those nodes and is given a name ETH. Here, designing a bridge circuit means finding the specifications for Vs and the impedance. The design procedure follows the Thevenin's theorem and finding the final Thevenin's equivalent circuit of this one. Here ETH is the Thevenin's voltage and ZTH is the Thevenin's equivalent impedance. Now let's assume the voltage source is connected between the nodes A and C and the output voltage ETH is taken from the nodes B and D. Now ETH is output voltage, that is where the measurement is taken. If the voltage measuring device has an infinite impedance, even though it is not practical, usually in mega ohm resistance range, we assume I is equals to 0. Now, from this configuration, the negative terminal of the voltage source is connected to the node A. So the potential at A is 0 and the potential at node C is Vs. Now, applying the Kirchhoff's current law or KCL at node B, we get Vb minus 0 over Z2 plus Vb minus Bs over Z3 is equals to 0, since we assume there is no current passing through the voltage measuring device. Simplifying this, Vb over Z2 plus Vb over Z3 is equals to Vs over Z3. Finally, solving for Vb or solving for the potential at Vb is equals to Vs times Z2 over Z2 plus Z3. Similarly, applying the KCL at D, we get Vd minus 0 over Z1 plus Vd minus 0 over Z1 plus Vd minus Vs over Z4 is equals to 0. Again, simplifying this, we get Vd over Z1 plus Vd over Z4 is equals to Vs over Z4. Finally, solving for Vd is equals to Vs times Z1 over Z1 plus Z4. Now, assuming Vb is at higher potential than D, even though this is personal, it depends on your assumption. You can assume the reverse, but assume that point B is at higher potential than D. And ETH equals VBD or Vb minus Vd. Substituting the previous values for Vb and Vd, we get this one. ETH is equals to Vs times Z2 over Z2 plus Z3 minus Vs into Z1 over Z1 plus Z4. Finally, we got the expression for ETH or the Thevenin's voltage across B and D is equals to Vs times Z2 over the whole Z2 plus Z3 minus Z1 over Z1 plus Z4. This is our final ETH expression or the output voltage expression for this bridge circuit. Now, to find the Thevenin's impedance, we need to replace the voltage source Vs by its short circuit and redraw the circuit like this. Now, we can find the Thevenin's impedance ZTH from the simplified circuit where Z2 and Z3 are connected in parallel and Z1 and Z4 are connected also in parallel. Those two circuits, the above and the lower, are again connected in series. Now ZTH equals this one, Z2 times Z3 over Z2 plus Z3 plus Z1 times Z4 over Z1 plus Z4. This is the Thevenin's impedance. Now, we can draw the simplified Thevenin's equivalent circuit like this, where ETH equals Vs times Z2 over Z2 plus Z3 minus Z1 over Z1 plus Z4, and ZTH equals this one. Now, when we come to our sensor's Wheatsone bridge, all the three impedances are purely resistive. R2, R3, and R4 are purely resistive, and our sensor is also RT resistive. Therefore, by replacing all the Z's by their corresponding resistance, we can write our previous ETH by this expression, and the equivalent impedance is also replaced by RTH, and this is its expression. Now R1 is our sensor replaced by RT. Now this is our sensor's Wheatsone bridge. Now our design procedure or our Wheatsone bridge design task requires us to find the value of Vs, R2, R3, and R4. The current passing through the sensor RT, IRT equals Vs over RT plus R4. Those three equations govern our Wheatsone bridge design procedure. Our task now is therefore to design a Wheatsone bridge with a voltage source given as 5 volt, and our Wheatsone bridge is balanced at 25 degrees centigrade, and the maximum current passing through the sensor is 0.1 ampere. From our datasheet in video 2, we have a maximum power dissipation of 500 milliwatt, and this equals to 0.1 ampere. So those are the specifications, and we need to design our bridge circuit in a way to meet those specifications. Okay, now let's come to our analytical perspectives. We have ETH is equals to this one, and after some rearrangement, we get this one. Next, from this equation, the Thevenin's equivalent voltage ETH is minimum at RT minimum, and similarly, ETH is maximum at a maximum. From the given specifications, the bridge should be balanced at 25 degrees centigrade. What it means is that the bridge gives ETH is equals to 0 at 25 degrees centigrade. Our thermistor gives RT is equals to 1.5 kilo ohm. This is from the datasheet. Now, equating our ETH equals 0 at this resistance value, we get by rearranging R4 is equals to 1.5 kilo ohm times R3 over R2. The maximum current passing through the sensor is 0.1 ampere. We get maximum current where RT is minimum. Therefore, IS maximum is equals to BS into 1 over RT minimum plus R4, which must be less than or equal to 0.1 ampere. We have RT minimum from our video 2. We have the minimum resistance of a sensor at 50 degrees centigrade, which equals 0.6005 kilo ohm. So IS maximum equals 5 over 600.5 plus R4, which must always be less than or equal to 0.1 ampere. Since resistance is positive, this expression is always less than or equal to 0.1 ampere. Therefore, this requirement, IS maximum less than or equal to 0.1 ampere, is always guaranteed in our sensor. So, we need to find R3, R2, R4. Here from this equation, R4 is equals to 1500 times R3 over R2. The designer has a freedom of choosing resistance values as long as he or she can guarantee this relationship. But the ratio R3 over R2 determines the nonlinearity of our bridge circuit. From the expression of ETH, we have seen that ETH is a nonlinear expression, and this ratio R3 over R2 determines the behavior of the nonlinearity. So choosing a suitable ratio R3 over R2 is crucial. For example, by setting this ratio is equals to 10, we get this type of graph. Let's take also another ratio, R3 over R2 is equals to 5. And this is new relationship between T and ETH. Next, let's assume this ratio to be 1. And this is the behavior of the graph. Again, let's assume this ratio to be 0.5. And this is the curve. Thus are now the four graphs obtained by setting R3 over R2 different values. As you can see from the plots, the sensitivity and the linearity varies. From those four options, I get, for example, better linearity, sensitivity. I choose R3 over R2 is equals to 1. And let's take the graph. Now, this is the graph representing the relationship between the temperature T in degrees centigrade and the voltage ETH by setting the ratio R3 over R2 is equals to 1. Or in other words, by setting R3 is equals to R2, where the temperature varies from -5 degrees centigrade to 50 degrees centigrade. By using the formula we derived previously, at -5 degrees centigrade, ETH equals minus 1.4491 volt, and at 50 degrees centigrade ETH equals 1.0706 volt. Now let's compute the ideal relationship by using those two endpoints, or find the straight line relationship between those 2 points. Now let's find the slope, which equals 0.0458 volt per degree centigrade. Now find the equation by using one of the points and get this one. Y is equals to 0.0458 x minus 1.2194. And substitute ETH in place of y and x, t in place of x, we get ETH ideal is equals to 0.458 t minus 1.2194. The actual and the ideal relationships are drawn in the same plot like this. Now, as you can see from the plot, the actual and the ideal curves are more close. Let's see the nonlinearity at a temperature 10 degrees centigrade. Find the actual ETH at 10 degrees centigrade is minus 0.7589 volt, and the ideal value is minus 0.7614 volt, and the nonlinearity or the difference between the actual and the ideal values is 0.0025 volt. Substituting in the nonlinearity as a full-scale deflection equation, we get 0.0992% nonlinearity. The nonlinear behavior of the thermistor alone is higher at this temperature. You can check our video 2 in our sensors and their microcontroller interfacing video series. The nonlinearity of a thermistor without the bridge at 10 degrees centigrade was 28.89%. But here, look how much we reduced the nonlinearity by choosing a proper ratio R3 over R2. From the relationship of the sensor, thermistor has an exponential nonlinear relationship between temperature and resistance, and the bridge also has a nonlinear relationship, but we design our bridge in a way to reduce this nonlinear behavior. Now, let's look our bridge circuit for our thermistor. We have a voltage source base is equals to 5 volt, and we set the ratio R3 over R2 equals 1. So you can choose any value of resistors, R2 and R3, but for my case, I chose 200 ohm for both R2 and R3, and we set R4 is equals to 1.5 kilo ohm, and our RT has this relationship. So our Wheatsone bridge design is completed here. You can watch our next video to see the behavior of this bridge in a Proteus software environment, and in our video 4 we will design an amplifier or set the output voltage to a predefined values.
Okay, thanks for watching. Don't forget to like this video and subscribe the channel. Feel free to leave your comment.